Alright, so welcome to some NASA Exoplanet Archive Exoplanet Transit Survey Kepler Search data site tutorial. I'm your host, your teacher. I even have my trusty cup of coffee with me in case I need it. Your first goal is to go to the NASA Exoplanet Archive Exoplanet Transit Survey Kepler Search website, which is on the Canvas webpage. And when you open it, you will see something that looks like this. The very first entry field here is for the Kepler ID. A Kepler ID is the identification number of one of 100,000 different stars that the original Kepler mission was monitoring every 30 minutes. And lo and behold, they're very friendly and kind here, and they give you a couple of example stars you can play with. You should try both of them. I'm going to enter the first one by just copying and pasting it. It's number 757076 in the Kepler ID. And when you have that entered, you can literally just click the View button here on the right, and it will bring you off to the data set for that star. And what it gives you is a results table that contains a list of 18 entries, and these entries are of 18 individual time series of collections of photometry of that star, photometry being a measure of its brightness at a particular time. So each of these time series contains hundreds of different readings of this star's brightness. So you can look at each of the column. You can see that there's a counter for all 18 of the time series, what the star name is, what type of cadence was used, and we'll talk about that. That has to do with the timing of the exposures. The dataset quarter. All of the datasets were downloaded at the end of every quarter, and some quarters had better data than others. The object status is a 0, meaning it does not have an exoplanet that we know of. Its right ascension and declination are the latitude and longitude in the sky for this object's location. Remember that the Kepler field of view is about 20 by 20 degrees, pretty big. The start and end time of these data series, the G, R, I, and Z magnitudes for this star on average, and then all sorts of other tidbits of information all the way out to the end where it starts getting into the radius of the star and solar radii, the metallicity of the star's atmosphere composition, the gravity of the star, the effective temperature in kelvins. All this stuff is pretty cool information. So let's go look at it. You can click on any one of these areas here on the left that says PDC SAP time series. Just click on any one of them. It all brings you to the same page. The page that comes up after some time, because it's going through and crunching a lot of numbers and extracting a lot of stuff from the data set, brings you up a plot of the brightness of the star over time for all 18 of these time series in one big plot. So if you count each of these individual rows, you have 1, 2, 3, 4, 5, 6, 7, 8. I think you should get 18 of them, right? They're all color-coded, etc. But this doesn't give us enough information to actually determine what's going on in the star. You can see that every single quarter that the overall flux or the brightness of the star seems to have bounced around considerably. Say from here to here, it has gone up considerably. And that is not because the star actually got brighter. It's because the star is actually on a different position on the CCD chip, which is a monster CCD chip of the Kepler spacecraft. So it's measuring a relative flux, and as long as it keeps the star centered on one particular group of pixels, then we can measure this variation in brightness. Remember, they're looking for exoplanets, and exoplanets that are transiting in front of the star will make the star appear a little bit fainter in a periodic fashion. So let's look at one of these in a little bit more detail. If you want to look at a periodogram of a given sequence, let's choose number 10, as we can, and then say compute periodogram. Now this is somewhat of a mystery, but first a break. It says the periodogram can take a long time to process. Sometimes it does, it can take minutes. These are pretty quick though on this particular star. So a periodogram looks at the data set and it actually tries to perform what is called a fast Fourier analysis on the data, brightness over time. And it looks for pulsations or periodicity in that. if it finds a periodicity, it will give you a high probability of periodicity measurement, like this incredibly good spike right here, which is showing us the period of the star's vibration or pulsation, or maybe an exoplanet orbit, causing a very periodic change in its brightness with a given periodic amount of time. And here's the time on the x-axis, and this is just under a day. It's 0.36 of a day. And then the power is a relative terminology. It means how likely is this to be a really good period. And it turns out the higher the number of the power, the more likely it is to be a true and honest to goodness period. Narrow ones are generally much better than fat ones. Fat ones over here are pretty questionable in terms of their accuracy and periodicity. Still, this periodogram provides you with all that information for good ones and bad ones. So here's the ranking number one period of choice is 0.362618 of a day, with a really good power of near 500. It's 497.065475. Ignore the p-value for now. And then it gives you a link to what's called a phased curve. And it does that for all the other periods as well. But the most notable one, which is higher by many orders of magnitude here, is the first one with a period of 0.36 of a day. A phased curve, which is what I'm going to click on in just a second here. A phased curve is an attempt by the software here at the NASA website, Caltech and NASA, to take all the data from this data set and then to overlap all the data by 0.36 of a day so that we can see how periodic it really appears. So we're literally taking the data over many days and just like crunching it into 0.326 of a day to see if it fits. If it doesn't fit, you'll know it. If it does fit, it looks pretty cool. Kind of like this. I suspect this is going to look really good. So here's a plot of the data at 0.36 of a day. And look at that. It's a nice pulsating star. You can tell that it's getting larger and smaller and larger again. This star is has a little bit of vertical flux variability. So the y-axis is its brightness, which light is actually coming toward instrumentation. There's some spread vertically in this because it is a pretty faint object. So that's not real. That's actually kind of a fuzziness to the determination of the accuracy of the brightness. But the horizontal, the phase, is perfect. So the phase is basically time. Every 1.0 of a phase is 0.36 of a day. Okay? So this is showing us that it has a very nice, sturdy 0.36 of a day pulsation. So folks, that is how you do this. You now can analyze hundreds of thousands of stars on your own free time. And we'll be discussing a project that involves this very thing. And we'll get to that as soon as I get back. Okay? If you have any questions, feel free to email me. You know how to reach me.